This is the last of the bonding models that we're going to look at, molecular orbital theory. It is the most complicated and also the most accurate. We're going to just stay on the very surface of it. We're not going to go into all the math of it. In molecular orbital theory, we look at orbitals for the entire molecule instead of just for atoms. So with the Lewis dot structures, the Lewis model, we represented electrons as dots and we put them around individual atoms. With the valence bond theory, the electrons were also localized on particular or between particular atoms. In the molecular orbital theory now we have an opportunity for things to be shared throughout the whole molecule. So the Schrödinger equation is the basis of orbital shapes, I guess you could say. Unfortunately, we can't solve the Schrödinger equation except for hydrogen. So what we do is we just use a trial function. It's kind of a trial and error method. You put in a trial function and see how that works out, and then you adjust it. So they use computers to do this, calculating the energy of the trial function. And then, okay, well, let's try this different trial function. Oh, that made the energy lower. Okay, so we'll go in that direction. It takes a long time. But they optimize for the lowest energy. And this is all something that nature is excellent at, and we're just trying to figure out what nature's doing. But nature has the minimum energy for those orbitals all figured out. And we're just trying to figure out what it's doing. So what we're going to do is we're going to look at combining atomic orbitals into molecular orbitals. So Lcao stands for linear combination of atomic orbitals. And so this is a weighted linear sum of the valence atomic orbitals of the atoms in a molecule. So again, we're just looking at valence electrons. This is the simplest trial function that works reasonably well. So we take the valence atomic orbitals of all the atoms in the molecule, not just the two that are bonding, but all of them together, and combine them and make molecular orbitals. In valence bond theory, we're looking at hybridizing the orbitals on a single atom. Here we're doing the whole molecule. So many of these combinations are delocalized over the entire molecule, whereas hybrid orbitals remain localized on a single atom. So that's the biggest difference between valence bond theory and molecular orbital theory. So let's look at our simplest molecule, hydrogen, H2. So here's one hydrogen atom, here's another hydrogen atom. They each have one electron in the 1s orbital. Combining these, linear combination of atomic orbitals, combine these and we can end up with something that might look like this, and this is considered a bonding orbital because this is lower in energy than the individual atomic orbitals that it came from. Remember, atoms will bond if doing so lowers their energy, makes them more stable. So this is a bonding orbital. It's given the name sigma for its shape. If you were to look down the end, the internuclear axis is what they call it, from one nucleus to another, it would be spherical. Okay? And this is much like the sigma bonds we saw in valence bond theory. So this is called sigma 1s, sigma because it's spherical, and 1s because it is formed from 1s orbitals. Any questions yet? We can also add those in a different way. Do you remember constructive and destructive interference of waves, right? So you can think of this as adding the opposite phase or subtracting the same phase. And so the illustration has subtracting. So when you subtract those, you end up with something that looks like this. Here you have one phase on one side, the opposite phase on the other side, and a node in the middle. This is going to be higher in energy than the original atomic orbitals, and so this is called an antibonding orbital. If electrons are in here, that's going to raise the energy of the molecule and make it less likely that they're going to bond. This is called sigma star 1s. It is also spherical, symmetrical around that internuclear axis. The asterisk tells us it's an antibonding. Any questions? So we can combine these two orbitals in a negative way, basically thinking of it as subtracting. That's the destructive interference, and they're going to give us something like this. Or we can have constructive interference, and we'll get something like this. This is going to support bonding, and this is going to oppose bonding.
I apologize if I was writing when you already said this. What causes the destructive interference?
Well, it has to do with the phase. So it's not obvious in this 1s orbital that there's a phase, but it is a wave function, and so it does have phase. So it's easier to think about light waves or waves on water, and you can add them in phase where the peaks and troughs line up. I didn't leave myself much room. We'll stick it up here, and so that's going to give us something with higher amplitude. Or if we add them when they're out of phase, then they cancel out and we get a straight line. Okay, so that's the idea. It's hard to visualize because this is a three-dimensional wave function that's spherical, and it's like, what the heck, right? So it's this same concept, though. Okay, and I'm not going to make you draw these things. Somebody asked me that yesterday. Do we have to draw those? No, you don't have to draw those. So we draw molecular orbital diagrams. So this is a molecular orbital diagram for the hydrogen molecule, H2. So on one side we have the hydrogen atom with its atomic orbital. It's a 1s with one electron in it. On the other side we have the other hydrogen atom, 1s orbital with one electron in it. We've put this electron with a downward spin because they're going to pair up when they get together in the molecule. Then in between, we're going to draw the two orbitals that form. Just like in valence bond theory, if you take two orbitals and you combine them, you end up with two orbitals. You don't get three, you don't get one, it's always the same number of orbitals. So we get this bonding orbital that's lower in energy, the anti-bonding orbital that's higher. So we draw these molecular orbitals, and then we see, well, I've got one electron here and one electron here, two electrons, and then I'm going to put them in here. And we're going to follow the same rules. We're going to go in the lowest energy first. We're going to follow Hund's rule and fill individually with parallel spins and then pair up if we need to. Well, here there's the one orbital, and so we put our two electrons in there and we're done. So this is the molecular orbital diagram for H2. Any questions? The bond order is the number of electrons that are in bonding molecular orbitals minus the number of electrons in antibonding molecular orbitals divided by 2. So let's go back to the picture. So to find the bond order for this, we look at how many electrons are in bonding orbitals. There's one bonding orbital that's got 2 electrons in it. So bond order equals 2 minus how many electrons in the antibonding? 0. And we take that and we divide by 2, and that gives us 1. Okay. So the bond order for H2 is 1. If the bond order is positive, if it's greater than 0, a chemical bond will form. That indicates that the electrons are going to have lower energy and a bond will form. The higher the order, the stronger the bond. So if you have a bond order of 3, that's a stronger bond than one with a bond order of 1. If you have a bond order that is 0 or negative, then the bond will not form. So let's look at He2. You think He2 exists? What do we know about helium?
It's pretty stable.
Very stable. He's really happy. He doesn't like to just mess things up with other people. He's just happy by himself. So just from our basic knowledge, we would predict that this doesn't happen. We can look at the molecular orbital diagram, though. So here's one helium atom. It's got 2 valence electrons. Here's the other helium atom. It's got 2 valence electrons. 1s and 1s make these 2 orbitals, sigma 1s, sigma star 1s. And we put our 4 electrons in, there'll be 2 down here and 2 up there. Then we can calculate the bond order. There's 2 in the bonding orbital and 2 in the antibonding orbital, and so this gives us a bond order of 0, which says this is not going to happen. It doesn't. There's no He2 molecule. Any questions? Yes?
So I'm assuming it's the same for diatomic elements like nitrogen, oxygen, fluorine, chlorine, and all that. So how come phosphorus and sulfur, like they have the same amount of valence electrons as nitrogen, phosphorus does, but it
Doesn't form a diatomic? That's a good question. It does form a polyatomic molecule, but it's not P2. I think there's P4 and P8. There's red phosphorus and white phosphorus. And they are actually different molecules. And sulfur does that as well. But yeah, the answer to that's kind of complicated.
not one A material.
Not 1A material, no. We can also do this for some kind of funky looking ions. Well, what about He2 plus? This would be a polyatomic helium ion. That looks pretty crazy also, but let's draw the molecular orbital diagram for that. Well, the difference between this one and He2 is there's 1 less electron, right? So we have to pick one of these to be the ion, and just because we picked the one on the right. So this guy has 1 electron, this guy has 2. We stick these in, and we've got 2 in the bonding orbital and 1 in the antibonding orbital. And so now we get a bond order of 1/2. This is predicted to exist, and it does. It's not common, but it does exist. So this is a summary. We approximate the molecular orbitals as linear combinations of atomic orbitals. The number of molecular orbitals is equal to the number of atomic orbitals. When you have 2 atomic orbitals combining, you get a molecular orbital that's lower in energy and one that's higher. When assigning electrons, you fill the lowest ones first with up to 2 spin paired electrons. You do follow Hund's rule. You go, if you have 3 or 4 that are the same energy, you fill them singly with parallel spins, and then you pair them up. Okay, in the hotel analogy, that's people taking their own bed before they share with someone else. Stable bonds require a positive bond order. Okay, so we should be able to do things like this. Use molecular orbital theory to predict the bond order in H2 plus. Is the H2 plus bond stronger or weaker than the H2 bond? So we need to draw a molecular orbital diagram. I don't know why I have red. This should be blue. We'll do blue. Okay. So over here, I'm going to have hydrogen. And over here, 1s, I'm going to do H plus. This is H2 plus. And so we have to get the right number of electrons in there. So if I put a hydrogen atom and a hydrogen ion together, then I'll have the correct number of electrons. And then I'm going to draw the molecular orbitals. So the combination here is going to give me 1 bonding orbital and 1 antibonding orbital. So this is sigma star, 1s, and this is sigma, 1s. And then if we're feeling fancy, we can do the lines. It helps when things get a little more complicated. Okay, so electrons. We have 1 electron over there, the hydrogen atom. This hydrogen ion has no electrons. That's why it's plus. So then we look at our electrons and we put them in the orbitals. It's just kind of silly to even draw the stupid thing, but there it is. So these are the molecular orbitals, Mo. And these are the atomic orbitals. And then ideally you should have an arrow here with energy increasing as you go up whatever. So predict the bond order.
1 minus 2, or 1 minus 0 over 2.
1 minus 0 over 2. There's 1 electron in a bonding orbital. There are 0 electrons in antibonding orbitals. Divide the whole thing by 2, and we end up with 1/2. So that is the predicted bond order. The second question, is this stronger or weaker than the H2 bond? Weaker, because the H2 bond had a bond order of 1. 1/2 is less than 1, so this bond is weaker. Any questions? So we just looked at period 1 in the periodic table, hydrogen and helium. Now we're going to look at period 2, homonuclear diatomic molecules. That sounds all fancy, doesn't it? Homo means the same nuclear, same nucleus, diatomic, 2 atoms. So these are molecules containing only 2 atoms, and those atoms are of the same element. So we have to look at what happens next. Well, here's lithium. Where are lithium's valence electrons?
2s.
In the 2s orbital. So here we've got 1 electron in the 2s, and in the other lithium atom, 1 electron in the 2s. When we combine these 2s orbitals, they form molecular orbitals just like the 1s did, and we've got a sigma 2s and a sigma star 2s. We've got a total of 2 electrons, so we put them in the lowest orbital first, and we end up with this. So the bond order here is also 1. Bond order is the number of electrons in the bonding orbitals minus the number in the antibonding orbitals divided by 2, which equals 1. Yes?
So are we going to talk about like, the P portion?
We're going to go all the way to neon,
Okay.
Ne2. Yep. Next over, beryllium. So looking at a diatomic molecule of beryllium, Be2. Again, the overall diagram is the same. What's different is the number of electrons. So now we've got 2 electrons in each atom, total of 4. When we put those in, we've got 2 in the bonding orbitals and 2 in the antibonding orbitals. And this gives us a bond order of 0. This is predicted to be unstable, and that's true, consistent with experiments. Any questions? Now we get to the p orbitals. So there are 3 p orbitals, right? And they are perpendicular to each other, x-axis, y-axis, and z-axis. So what we're going to do is we're going to call this internuclear axis the x-axis, just because that's what they decided. It could have been y or z, but they decided to do x. So if I take a p orbital from the one atom and a p orbital from the other atom, I can interact these with constructive interference or with destructive interference. I can add them or I can subtract them. When you add them together, so here we have the blue and the red represent different phases. So the blue phase on top of the blue phase, then the blue phase grows. This part between grows. That's a bonding orbital. It's going to be lower in energy. We have a lot of electron density between the nuclei that's going to hold them together. If I add these out of phase, if I subtract them, I end up with something like this, where we have this big blank area of node in the middle, and this is an antibonding orbital. Are you okay with that? These are also sigma orbitals, because if you look down the end of these, they're symmetrical around that axis. So this is sigma 2p, and this is sigma star 2p. Okay. The other 2 orbitals add side by side. So py and py, we can overlap them, add them together where they're in phase. So here we have the reds and the blues together, and we end up with something like this. This is not symmetrical now on that internuclear axis. So this is called a pi orbital. And if we add them out of phase, we get something funky that looks like this, again with a node, and that's an antibonding orbital. So this is pi 2p, and this is pi star 2p. This is a lot like the pi bonds we saw in valence bond theory, right? Where there was side-to-side overlap, and the sigma bonds were end-to-end. So in that way, these descriptions mean the same thing. So that's the second one, and then the third one, the overlap, the combination is the same. The orientation in space is just rotated 90 degrees. But these are both pi as well. So pi star 2p and pi 2p. Any questions? So how are these ordered in terms of energy? So we've got these 2p orbitals, and we end up with sigma, sigma star, pi, and pi star, and what's the ordering of the energy? Well, they determine this by calculation, and it can vary. And so we're going to take sort of a general, broad approach. These smaller ones, boron, carbon, and nitrogen, have a different order than oxygen, fluorine, and neon. The general ordering is this. That's nice, but I like the picture better. Why do you like the picture better? Because I'm a visual person and I can see this. This like, yeah, what? I don't know. Okay, so let's look at the expected.
You cut it out and make paper airplanes.
You could. It does look like that, doesn't it? It's a diagram for making paper airplanes. So when these 2p orbitals overlap, we've got 3 atomic orbitals on this side, 3 on this side. We're going to get 6 molecular orbitals. So we get 1 p orbital from each side overlapping end to end, making sigma bond, sigma orbital, and sigma star. And then the remaining 2 do a side to side and make a pi and pi star. There are 2 pi star orbitals and 2 pi orbitals. And they're beautifully symmetrical. The sigmas are on the outside, the pi's are on the inside. The star one is always higher in energy than the corresponding one without the star. Because that's what makes it an antibonding orbital. So this is the expected order. Boron, carbon, and nitrogen mix it up a little. Why? I guess because there has to be exceptions. So what they've done is they've just switched these two. Sigma star, pi star remain the same. It's just taken these two and swapped the order. Okay? Down here we've got the 2s forming a sigma 2s and a sigma star 2s. That's exactly the same. It's just this that switches. So how do you remember that? Be careful now. Boron, carbon, nitrogen. If you're doing boron, carbon, or nitrogen, be careful now. You got to switch those the two bonding orbitals. Okay? So let's, oh yeah, this is the Y. So there's more mixing of the S and the P, and so that's what's causing this smushing around and this reordering. That's the Y. I really don't care about that right now. So here are orbital diagrams for the remaining period 2 elements. So here we've got boron, carbon, and nitrogen. They've got the pi 2p lower in energy than the sigma 2p. Oxygen, fluorine, neon, these are regular, and so they've got the sigma 2p lower than the pi 2p. That's the difference between these two groups. So it's because of that large interaction and the small interaction. I'm not going to quiz you on that. So boron has 3 valence electrons, right? So B2 has 6 valence electrons, and we put them in like this. 1, 2, 3, 4, 5, 6. This is Hund's rule. They're going to take their own orbital if they can. And you can calculate the bond order here. There's 2, 3, 4 in the bonding orbitals. So that's 4 minus 2 in the antibonding orbital. So that gives us a total of 2 divided by 2, and our bond order is 1. Carbon has 4 valence electrons each, so a total of 8 in this molecule. 2, 4, 6, 8. You can calculate the bond order, it's 2. Nitrogen has 5 valence electrons, so a total of 10 here. 2, 4, 6, 8, 10. The bond order for nitrogen is 3. We see a correspondence between increasing bond order and increasing bond energy. Bond energies were measured experimentally. And then the bond length, as the bond gets stronger, it pulls those atoms closer together. So nitrogen has the shorter bond length because it has the stronger bond. Okay? We keep going up. Now oxygen uses the regular ordering of these molecular orbitals. Each oxygen has 6 valence electrons, so we've got 12, 2, 4, 6, 8, 10, 11, 12. The bond order now is beginning to decrease. It's only 2. And we see that the bond energy also decreases and the bond length increases compared to nitrogen. Fluorine has 14 valence electrons, so it's going to look like this. And its bond order goes down to 1. And then here's neon. Neon 2 shouldn't exist, right? It's a noble gas. It's happy. It's got its octet. Why would it do this? Well, it doesn't. And this shows us the bond order is going to be 0. So we can't measure the bond energy or the bond length because it doesn't make this bond. Any questions? Stunned silence. Okay, so this is cool.
When liquid nitrogen is poured onto a magnet, the magnetic field does not affect the liquid. When we pour liquid oxygen onto a magnet, however, it is held by the magnet because oxygen molecules are paramagnetic. Paramagnetic substances have unpaired electrons.
You gotta watch that again.
When liquid nitrogen is poured onto a magnet, the magnetic field does not affect the liquid.
Just pour straight through.
When we pour liquid oxygen onto a magnet, however, it is held by the magnet because oxygen molecules are paramagnetic.
You get stuck.
Paramagnetic substances have...
You see it? It's stuck there. Wouldn't that be weird if you're pouring water through a magnet and it just hung there? It'd be weird, huh? Oxygen does
Paired
that.
electrons.
Just saying. I'll let I get it. Okay.
So one of them is paramagnetic and one of them is diamagnetic. And you can see that by the experiment. Which would be really cool to do live for you, but this was so much easier. So we know from the experiment we just saw, oxygen is paramagnetic. It must have some unpaired electrons, right? So here's the molecule of oxygen, the Lewis model, and we've got a double bond and we've got lone pairs. I don't see any unpaired electrons there. Here is the valence bond model where we've got p orbitals overlapping here and p orbitals overlapping here. We have a sigma bond and a pi bond, and then we've got lone pairs in the remaining orbitals. Do you see any unpaired electrons? No. Both of these models predict that oxygen would be diamagnetic and not stick in the magnet like it does. But I thought there was something else. When we look at molecular orbital theory, we see that there are 2 unpaired electrons. So this is an example of one of the things that led us past valence bond theory. It doesn't explain everything. So then you have to tweak the model. You have to come up with more ideas to explain what's actually happening. We still use valence bond theory because it's a lot easier to understand. We use Lewis theory a lot because it's just simple and it works much of the time. But molecular orbital theory is more accurate. Question?
Yes.
Okay.
Orbital theory addresses the valence electrons for the entire molecule.
Yes.
Okay, I got confused earlier. I was thinking all electrons before an atom.
No, molecular orbital theory is taking the valence electrons from each of the atoms and combining them into molecular orbitals. Yeah. So this question asks us to draw a molecular orbital diagram and determine the bond order for the N2 plus ion. Okay, so what are the valence electrons that nitrogen has? They're in the 2s and 2p, right? So we need to have 2p and we need to have 2s on each side.
Be careful.
Yeah, be careful now. Okay, so down here this is 2s, and we don't have to be careful when we combine those, but we just get a bonding and an anti-bonding from that one. But when we do the p orbitals, that's where we get, be careful now. And as usual, I didn't draw those very well. Need to move it up a notch. That'll probably end up being too high. Whatever.
Now we're drawing robots.
Yeah. Well, this kind of looks like maybe a cat that's smiling or something. It's this open mouth, and those are the cat eyes. I don't know. That's what I saw just now. So normal would be the sigma on each end and the pi's in the middle. That's normal. But this is nitrogen. Be careful now. And so we need to switch the order of these two. I did it again. What else did I do wrong here? I've got 3 orbitals here and 3 orbitals here. And how many boxes did I draw there? 8. I'm not used to drawing 2 boxes. This should be 2 boxes and 2 boxes, so we'll fix that. So this is just 2 boxes. And I need to switch the order of these two, so I need to erase them anyway. So this is pi 2p and sigma 2p and pi star 2p and sigma star 2p. I'm not going to do the dashed lines on the other side because it's a mess. Okay, so we're supposed to do N2 plus. So I'm going to put N on this side, and we need N plus on the other side so that we can get the right number of electrons. Everybody okay with that? So nitrogen has 5 valence electrons. 1, 2, 3, 4, 5. Over here, this nitrogen ion has 4. 1, 2, 3, 4. So we have a total of 9 electrons. And so we're going to put them in here, just like we filled the regular orbital diagrams back when we were talking about electron configurations. 1, 2, 3, 4, 5, 6, 7, 8, 9. Everybody okay with that? Determine the bond order, it says. So bond order is number of electrons in bonding orbitals. I've got this. I probably should have labeled those. So sigma 2s and sigma star 2s. So I've got bonding orbitals 2, 4, 6, 7. 7 electrons in bonding orbitals. And how many in antibonding? 2. And then that's divided by 2. So this gives me 5 halves, or 2.5. So that's the bond order for this ion. The bond order for nitrogen, if you don't remember, was 3. Is this stronger or weaker? Weaker. Because the bond order is less. 2.5 instead of 3. Weaker. Is this diamagnetic or paramagnetic? Paramagnetic, because we have an unpaired electron. Any questions?
Probably about 1,000 of them I think of tonight.
Yeah. Well, that's what texting is for. I'm just going to be sitting at a baseball game.
You must spend half your time.
Actually, I don't. It's very disturbing to me how few students text me.
Oh, here, I was
There's a handful that text me regularly. Yeah. And you, and there's a couple in the other class, but for the most part, no. So,
I was thinking to myself, I was like, this is such a valuable resource. I bet she gets texts all the time. I start feeling bad for texting.
no. So what happens if you text too much, or if I just don't feel like answering questions, is I just don't answer your text. Like sometimes I'm asleep. But people have gotten texts at like 3 in the morning because sometimes I'm awake. Okay, heteronuclear diatomic molecules. So these are 2 different elements making a bond. Things get a little more complicated here. One of the things that's different is that the energy of the atomic orbitals is not the same. So here we have one of my favorite molecules. No, I don't know where your chamber choir tuxedo shoes are, even though you're leaving for New York City tomorrow. I'm sorry, I don't know. No. Sorry, that happened last night. So nitrogen and oxygen. Nitrogen is less electronegative. Oxygen is more electronegative. Has more affinity for electrons. That means its atomic orbitals are going to be a little lower in energy than those of nitrogen. So that's why this is kind of cockeyed here. But we still get this combination from the 2s orbitals. We get a sigma star and a sigma. From the p orbitals, we get the sigmas and the pi's. Okay? Any questions? Funny thing with fluorine. Fluorine is the most electronegative element. It is so electronegative that all of its atomic orbitals are lower in energy than hydrogen's 1s orbital. You look at these, and it's like we don't even have the 1s orbitals on here, right? They're down here. They're lower than this. And these guys are, roughly comparable. But here, we've got hydrogen's 1s orbital is higher in energy than the 2p orbitals on fluorine. So that's kind of crazy. So what's going to happen here is that one of fluorine's atomic orbitals is going to interact with the 1s orbital on hydrogen. That's going to be an end-to-end. The first one is always a sigma, an end-to-end. And so we're going to get a sigma star and a sigma. Hydrogen doesn't have any other orbitals with electrons in them to interact with fluorine, and so we're just going to draw these over here just sitting there with the lone pairs. Okay, yeah.
So fluorine and hydrogen, purely based on the valence electrons, looks like it gets together and has a real good time.
Yeah.
But based on molecular orbital theory, you see that there's actually a lot of bottom orbitals going on, making it.
Well, this is a bonding orbital. These are non-bonding, but they are not anti-bonding. So when you calculate the bonding order, it'd be 1/2. We've got, 2 minus 0 divided by 2 is 1. Yes, it would be 1. Yeah, because these are non-bonding. They're neutral. It's like we're not contributing to the bond, but we're not opposing it either. We're Switzerland or Canada, right? Just kind of here.
So how do you, I'm probably just having a break for a moment, how do you determine the difference between non-bonding orbitals and antibonding orbitals?
Well, I think this is the only picture we're going to show you like this.
Okay.
Yeah. So this one and that one, we're just kind of giving you an overview of these are the kinds of things that we have to think about. We're just, we're at the tip of the iceberg, and there's just all this stuff underneath, and we're not going underwater. We're going to stay on top. But we should be able to do things like this. Use molecular orbital theory to determine the bond order of the FO minus ion. Is it paramagnetic or diamagnetic? So FO minus. So we've got a fluorine and an oxygen, and so we're going to draw their atomic orbitals first. Let's see how to space this out. So we've got 2s and 2p. And the s orbitals are going to make a sigma star 2s and a sigma 2s. And then those p orbitals are going to make sigma and pi molecular orbitals. What's the order of them going to be? Do we have to be careful now?
Yeah, this is oxygen.
Be careful now. BCN.
Oh,
Never mind you. It's okay.
I heard now. I'm like, oh, is it now?
So we've got our nice symmetrical arrangement with the pi's in the middle and the sigmas on the outside. So I'm going to put fluorine over there and oxygen over here. Now, in terms of number of valence electrons, what does that minus sign do? It adds an extra electron. It doesn't really matter which element you give it to, because all we're really worried about is what's happening in the middle. Yeah?
That very bottom one, should it be sigma 2s?
Yeah, it should. Thanks. Who do you think would want the extra electron more, fluorine or oxygen? Fluorine. It's the most electronegative. So I'm going to give it to fluorine. So fluorine had 7. I'm going to give him the extra one. So I'm going to draw 8 for fluorine. And that makes him the F minus. That's flunking really badly. Got an F minus. And oxygen's got 6. 1, 2, 3, 4, 5, 6. What's really important is the total number, which is 14. So then we fill in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So bond order, how many in bonding orbitals? 2, skip that one, 4, 6, 8, right? So 8 minus how many in antibonding? 2, 4, 6. So 8 minus 6 over 2, we get a bond order of 1. Should this ion form? Well, just look at the bond order. Should it form? Is the bond order greater than 0? Yeah. So it should form. It would be hypofluorite, which is not a common ion, but it can form. A lot of these things that can form, I mean, yeah, we can make it in the lab. We can, like Li2, a metal, diatomic metal, that only happens in the gas phase. All these are crazy things we're looking at.
Why?
Because, that's a good question. Why are we looking at these crazy things? Because these are the simplest molecules there are. And we don't want to go past diatomic molecules, and we don't want to go past period 2.
Okay.
Do you want to add d orbitals?
Not really.
No, that sounds messy.
Are we going to add D orbitals?
No, we're not. We're almost done. Okay, so there's our answer to the bond order. Is it paramagnetic or diamagnetic? Diamagnetic. All of the electrons are paired. Diamagnetic means it would not be attracted to a magnetic field.
So we just look at the middle one when we do that one?
Yeah, you're just looking at the molecular orbitals to answer the bonding order and whether it's diamagnetic or paramagnetic. So we are just going to talk about polyatomic molecules and why we need to tell you anything about molecular orbital theory. So Lewis model and valence bond theory do not explain some things that are really important. And if you're going to take organic chemistry, they will become important to you. So here's ozone. Here's the Lewis structure. We did that earlier, ozone. And we're like, it's resonance. It's actually between. We know experimentally that this bond length and strength is the same as this one. But we're drawing it like this. It's more like a 1.5 bond. Valence bond theory can't handle this either, because it can do a double bond between these two oxygens and a single between the other, and it can't do the resonance either. But molecular orbital theory can. What is that? That's ozone. So in ozone, we can combine those p orbitals into molecular orbitals and delocalize them over the entire molecule. These oxygen-oxygen bonds are equivalent now. And that's what we know from experiment, that the oxygen bonds are equivalent in ozone. We don't have to understand how it does that in molecular orbital theory. We just need to say, it works. So cool, that's awesome. Let the PChem people figure that out. Here's another one, benzene. So benzene is a 6-membered carbon ring, and in Lewis structure we have alternating single and double bonds, but there's resonance. And valence bond theory doesn't do this any better, and it's just really messy to look at, so we didn't even draw you the picture. Molecular orbital theory takes those electrons and delocalizes them over the entire molecule. And so this helps us to understand the stability of benzene and how it's symmetrical. We have these pi clouds above and below. Kind of looks like a trampoline for the swimming pool or something. We need to have a basic understanding of how this can happen later when you take organic chemistry, because there's a lot of this stuff that goes on, and if you don't understand it, it's going to be rough. Okay, so electrons can be delocalized over the entire molecule.